10 minutes by bus. There is a radioactive also that they say it's very healthy. It's a very low dose. I don't think it's healthy, but I don't think it's also harmful. It's a very low dose, but the Japanese believe. But it's a really long thing. 1,000 meters down the pipe, actually, very deep. It's slightly radioactive.
Yeah, so
And it's always empty.
Okay, I think we can start. First of all, thanks everybody for coming. I see there's quite a few. I wanted to, before we start, just to emphasize that on Saturday there's a train strike. I received emails, I think, only from 2 people who have flights from London. If you're not flying from Newcastle, then and you're flying on Saturday, we have to deal with that somehow. So please come and see me, and we'll figure out a solution. Either you go on Friday and book a hotel in London or wherever you're flying from, or we do something else. I just want to remember saying that because I'll forget. Yes, so I'm very happy to open the 3rd installment of this workshop. The previous 2 were really great. The first one was only online. The second one was much better, and the third one, hopefully, it'll be even better. Without further ado, I will introduce Michael Levin, who is going to open the workshop. The talks are 2 hours slots, and as I explained to the speakers, this is not to be construed like a packed 2-hour talk, but something a little bit more leisurely. You can take a break, Michael, if you want, at any point where you feel, give us a little bit of a breather. And please do ask questions, and ask them early, because we don't want any speaker to have run away from us, and then it's a torture. Like, then it's a 2-hour torture. But if we stop them in time, then it can be very educational and fun for everyone. So please feel free to have mini discussions. This 2-hour talk is precisely for that reason, so that we don't have, let's discuss this after a talk. Of course, that can also happen if it's a longer discussion, but I want to minimize that. I want things to be as clear as possible during the talk. So without further ado, Michael, please, you have the floor, and let's get going.
Thank you. Yeah, first I just want to thank the organizers for putting together this really interesting workshop. I'm really looking forward to hearing what everyone's doing. Today I was going to talk about some more recent work on topological entanglement entropy.
So apparently the audio is not well enough, so we'll probably have to use this. Do we know how to use this? Does somebody know?
I just have to turn it.
Yeah, I think so. Is it on the top?
On the top. Or is it this red button?
So physicists can speak about whatever. Theoretical physics cannot replace a ball.
No?
The theoretical physicists are useless. They cannot turn on. Now he will go, he will press something, and it will work. But
Yeah.
50 people cannot replace a ball. It's not true.
Is that working? Yeah, okay.
Yes.
Okay, yeah, so I was going to talk about some sort of more recent work on topological entanglement entropy. The title of my talk is Lower Bound topological entanglement entropy. This talk will be partly based on a paper that we put on the archive earlier this year there's this paper we put on arXiv, and this is work done in collaboration with Isaac Kim and Lynn and Bard and Owen Sheik. So it's going to be partly based on that, but some of it, this part of it's actually some unpublished work that I'd say related to that paper. Okay, so before I get into this lower bound, I first have to tell you what topological entanglement entropy is and set up the basic problem that we're interested in. So first, let me just tell you the setting for this talk. So the setting for this talk, well, okay, the global picture before I get to the setting is topological entanglement entropy, as many of you may know, it's a way to detect anions by looking from a ground state wave function. So given a ground state wave function, you can compute a certain quantity involving entanglement entropys at certain regions, and this quantity is supposed to tell you whether you're dealing with a state whose excitations are anions. Okay, that's the idea. So it's a way of detecting topological anions, or you might say topological order, from a ground state wave function.
So does that mean it's only well defined in 2 + 1?
Yeah, so this is in 2 + 1 dimensions. Thanks. Yes, the whole talk is going to be about 2 + 1 dimensions, although people have talked about generalizations to 3 + 1 dimensions as well. But yeah, thank you for asking. Everything's going to be 2 + 1D. So in fact, let me start off with just the setting for this talk. So not only am I going to be talking about 2 + 1D, but I'm really going to be focusing on lattice models. So the setting for this talk is lattice models. And actually more specifically, you could say bosonic or spin models. So basically what I have in mind is some lattice, we could just imagine just a square lattice for simplicity. Each site there's some finite dimensional Hilbert space. So you could think of these points as, say, spins or some other local bosonic degree of freedom. Okay, so the Hilbert space is going to just be a tensor product. So if I call my Hilbert space V, it's some tensor product, little v, tensor, little v, tensor, little v. It's supposed to be a script v. I don't know if I accomplished that. Okay, so it's just a tensor product Hilbert space, and the Hamiltonian, the kind of Hamiltonian that I would be interested in, is just a pretty much generic local Hamiltonian. So the Hamiltonian can be written as a sum of local terms h sub I, where each term h sub I acts on some small number of spins, like this. Okay, so I'm interested in a tensor product Hilbert space with local, and then Hamiltonian with local interactions. Okay, and in particular, we're not just going to be interested in generic. Within this class of sort of generic Hamiltonians, we're going to be interested in Hamiltonians which have a gap. So we're going to be focused on what we would call gapped lattice models. And what I mean by gap is, of course, that if you look at the energy spectrum, we're interested in a system where you have a ground state, let's just say for simplicity, unique ground state, and then you have a bunch of excited states. And there's some gap separating the ground state from the excited states, and this gap should remain finite in the thermodynamic limit. Okay, so the limit of a very large piece of lattice. So that's the set. We're going to be interested in gapped lattice models. Now, within this setting of gapped lattice models or gapped many-body systems, there's a very interesting phenomenon which probably almost all of you are familiar with, which is that some gapped many-body systems have anion excitations, right? So let me just quickly remind you about that. So anions. So what that means is that you have a gap system, and you can look at excitations above the gap, and in some of these systems, you find localized excitations, which are like particle-like excitations. And particle excitations, if you have, say, two of them, two identical such particle excitations, and you exchange them, they don't give you the phase, let's say, +1 for bosons, or even -1, like you would get for fermions. Instead, if you exchange them, you get some other phase. In fact, you can get almost any phase. That's why they're called anions. So the picture here is, you exchange two anions, you get some unusual phase, or relatedly, maybe even more, even a better way of saying it is if you take one anion and you braid it all the way around the other anion. So that's kind of equivalent to doing two exchanges. For fermions or bosons, you wouldn't get any phase at all. But for anions, in particular abelian anions, which is what I'm talking about right now, if you braid one anion around the other, you'll get some phase, and it'll be some phase different from one. Okay, so that's the abelian anions, where braiding one particle around the other gives you some phase. Of course, you can also have non-abelian anions, which are even more exotic types of excitations. Sometimes in these lattice models, you find excitations which have this really unusual property where if you have a couple of excitations, let's just say 4 of them, there's no longer a unique ground state. So you can think of these, the way I like to think of these anions is I actually like to think of them as not excited states of my original Hamiltonian, but rather ground states of a kind of new Hamiltonian. You can imagine taking your Hamiltonian and adding some trapping potential, that traps the particles in these wells. And for an appropriate trapping potential, this, what we might call an excitation, the original Hamiltonian will actually be the ground state of this new trapping potential. So what's interesting for non-abelian anions is if you put in, you trap your particles in these 4 wells, you find not a unique ground state, as you might find for abelian anions, but you might find multiple ground states, say 2 ground states. Again, they're separated from all the excited states by a gap. And then what's special is not only do you get this degeneracy, but if I now take 2 of these anions and then, let's say, braid one around the other, for example, trapping it into a potential well and adiabatically moving the potential well, I won't get a phase, I'll get a unitary transformation, which acts on this 2-dimensional subspace, and that unitary transformation is different from the identity. Okay, so that's the non-abelian case. And in general, these unitary transformations don't commute from each other on different pairs of anions, hence the word non-abelian. Okay, so these are the types of things you can get, abelian or more generally non-abelian anions. And these types of excitations, there's a lot of mathematical data describing them, which I won't get into, describing the phases you get when you braid things or when you fuse anions together. And that data is well understood, and it's you can sometimes call a unitary modular tensor category, or if you're sort of more field theoretical, you might call it a topological quantum field theory. So the properties of all these anions are described by a topological quantum field theory. And so one way of saying that some many-body systems have anions is equivalently, you could say some many-body systems at very low energies, they're described effectively by some topological quantum field theory.
Are we considering both bosonic and fermionic systems?
So what?
Are we considering both bosonic and fermionic
You know what,
systems?
for simplicity, only bosonic systems. So I said that Hilbert space is a tensor product, although actually almost everything I say will generalize to fermions. It's just simplest to think of the bosonic case where you have this simple tensor product structure.
Your statement about the ground state density, this is assuming you're on a sphere.
Which one? Which statement?
With the non-abelian anions.
Why do I have to be on the sphere?
Or with the abelian anions, you said the ground state density would be 1.
Yeah, or you could either imagine you're on a sphere, or you could imagine you're in a disk or a plane or something.
Yeah, like if I was on a torus and I have some abelian anions trapped, I could have.
Yeah, I don't want to consider. Yeah, that's right. So it's indeed true, and even here when I say unique ground state, some of you might have gotten worried because you're used to thinking on a torus or something. So actually, for this purpose of this talk, maybe we're just thinking on an infinite plane or on a disk.
Okay.
You could put on a sphere if you get worried about thinking about an infinite plane.
Okay, great. Thanks.
Yeah. Any other questions? Okay, so some gap body systems that have anions, it's described by TQFT. And now, okay, the TQFT, or if you want, or more concretely, the anions and all their properties, these are universal properties of your state. So what I mean by that, so let me just write it down and see what I mean. So this TQFT, or equivalently sort of the anions and their properties, these are universal property. Not just by universal property, it's not a universal property, the state's universal property of the whole gap phase. And what I mean by that, I don't want to go into a lot of definitions, is we can say 2 lattice models belong to the same phase if you can tune the parameter in your Hamiltonian, interpolate between the 2 Hamiltonians while maintaining the gap, okay? And so the claim here is any 2 Hamiltonians that can be interpolated between them, so i.e. any 2 Hamiltonians that belong to the same gap phase will have the same anions and the same TQFT, okay? So that's what I mean by universal. It's not just specific to this state, it's a property of the whole phase. And when you have a property like this, that's a property of the entire phase, you can argue on very general grounds that this property must be a property that you can, it only depends on the state, not on the Hamiltonian. In other words, you should be able to read out, in principle, the TQFT and all the anyons just from the ground state itself. So it must be encoded in the ground state. All this TQFT. And that's common in condensed matter because it's at least to even use that language when we talk about phases of matter. When we talk about, we often say a particular state, the Laughlin state has anion excitations, right? Or the toric code ground state has anion excitations. So very generally speaking, actually any property that holds for an entire phase is something that you can associate with the state. You must be able to extract it from the state. And so there must be some way, we know on general grounds, there must be some way of taking the state and computing all the anion properties. So the kind of basic problem we have is we can, and actually more generally, at least in the case of anions, it's clear that they're kind of a local property, right? It's like you just need to take two anions in a disk and braid them. So you should be able to take just a local patch of your ground state. You know, here's a bunch of spins. And just knowing the density matrix in this local patch, rho, you should be able to read off the whole TQFT, get everything, all the anions, all their properties, everything. Okay? So that should be possible, but the question is how? How can you do that? And you might also ask why you want to do that. And I won't say that much about that, but you know, I'd say it's interesting both for conceptual reasons to be able to work directly with the state and find the TQFT. It's kind of conceptually cleanest to be able to go directly from the state, not have to use the Hamiltonian. The Hamiltonian is a bit superfluous when you're dealing with gap phases of matter. So it's conceptually nice to work with the state. It's also maybe useful practically in many numerical algorithms. The state is the easiest thing to get, the ground state. So it would be nice to just directly figure out the TQFT from the state. So that's kind of the basic problem. How can we, from a ground state, determine some properties of our anions? Preferably, we'd like to get all the properties, but how can we get even some of the properties?
Question?
Yeah.
This question may not be directly related to the talk, but it's related to this general theme. Mm-hmm. Suppose I consider gapless states. Suppose it's some gapless state with dynamical exponent unknown. How do I figure out the dynamical exponent?
Yeah, I'm not sure if that's possible. That's why I emphasized here. It's a good question, but I'm not sure if it's possible. But here I'm saying specifically for gap states and specifically for properties, you might call these so-called topological properties, properties that are universal to the entire phase. For such properties, you can argue they must come from the state. Yeah.
How do you talk about a gap or excitations without talking about one?
That's a good point. So we have to assume that the state has some Hamiltonian. So basically what I'm saying is suppose your friend gives you a state and says, I promise you, this is the ground state of some gapped Hamiltonian. Then I'm claiming it's a completely well-defined problem to say what's the anion content of that state. And actually, in some senses, this follows from a very simple observation, which is that if you have a gapped ground state and you happen to find two gapped Hamiltonians that have the same ground state, you can interpolate from one to the other without closing the gap. In fact, it's just a linear interpolation. So you know those two Hamiltonians have to belong to the same phase if they share the same ground state, and therefore, because I postulate that since I claim this is a universal property, they must have the same anion content. So it actually just follows from that logic. But in principle, your friend doesn't have to tell you the Hamiltonian. They just tell you the state, and it doesn't matter what the Hamiltonian is. That's kind of a very general way to argue it. You can also very more specifically think of anions as sort of defects in the ground state. They're little localized regions where the ground state's been deformed. From that point of view, it's also kind of clear that just given the ground state, you can find all the defects in the ground state and find all their properties. So in principle, it's kind of possible to argue. In very general grounds, it's possible to argue you can get all this information, but the question is, how can you do it in like a nice way? Yeah?
Is this conjecture also generalized to higher dimensions?
Which conjecture? I think, yes, that would be expected in any dimension, yeah.
If your friend hands you a ground state and promises you that it comes from something gapped, could you tell if they're lying? Could you tell them secretly gapless?
I mean, that's a great question. That's a great question. I mean, obviously, sometimes you.
So something should go wrong in the argument, right? In that situation.
With what argument?
Naively, right? It's just,
well, your question of like, is there a way to characterize what a gapped ground state is just in terms of the state is a very interesting question, and I don't know if it's fully known. Obviously, we know certain properties of gapped ground states, like they have short-range correlations. So that's the first thing I would do is I would check whether the state has short-range correlations. If it doesn't have if there's some long-range, like power law type correlations or something, I know my friend is blind. But actually beyond that, there are very few things that you can check. That's
And,
a really
is
good
there
question.
an assumption of translational symmetry here? Or is that not important?
You don't really need translational symmetry here. I mean, the only way in which it might come in just a limited way is like, ultimately you kind of need to take some kind of limit of arbitrarily large system sizes. Otherwise, you can't really talk about any of these things like in a sharp manner. And so you have to have a sequence of larger and larger system sizes. So basically, if you want to be really formal, the person can't just hand you a state, they have to hand you kind of a sequence of states in larger and larger disks or something, right? And often that's easiest to do if you have translational symmetry, right? Because then you can define a Hamiltonian in larger and larger systems. But that's the only sense in which translational symmetry would be useful. It's just sort of being able to define a thermodynamic limit in a very simple way. But I don't think it's
And also,
necessary any more than that.
I mean, once you allow to access such observables like entanglement entropy, you're basically allowing to compute partition functions on non-trivial manifolds. So that's the same as, I mean, we know that we can extract the TQFT from that.
Well, I don't know. I mean, I'm not sure. Like, especially when you're dealing with lattice models, it's totally unclear, at least to me, how to even make sense of what it even means to talk about a partition function on some general
I'm just
surface.
saying the continuum language. This is the same.
Yeah, no, it's true. You might be able to motivate. You might be able to motivate some of these things, but actually, the whole point of this talk is to show you that you have to be very careful with such kind of thinking. Like, so I'm going to tell you about topological entanglement entropy as a way to do this, and I'll tell you how it doesn't quite work in some sense, and that has very specific. Hopefully, that will show you that you can't just use continuum thinking to you can get sort of wrong answers. Other questions?
So in this argument, is locality important?
Which are?
PQFT enums are universal property of a state.
What do you mean that it's what locality? I'm certainly thinking about local Hamiltonians. That's
yeah, suppose you just have a Hamiltonian without knowing whether it comes from a local Hamiltonian. Sorry,
oh yeah, it has to come from a gapped local Hamiltonian to make this. Yeah, locality is very important to everything in that sense. Okay, any other questions? Okay, so, all right, so that's the problem. Okay, so then I'll tell you one proposed, oops, I see. So there
It doesn't work.
Doesn't work, okay. It's fine.
You have to put it down and then this one up.
I see, but this other one doesn't even move, right? So maybe it's not
So
even that helpful.
you can put it down or raise this one up.
You know what I'm going to do? I'm just going to erase over here. I think that's easier. Because, I think we... Okay, so...
Yeah, you see, Michael, there's a lower one which you can pull up. Yeah,
I
just
see,
pull it up.
But what I was thinking, though, is I do want this one to be shown. Maybe what I want to do is do over here.
Yeah, you just
Swap them.
just swap them. Exactly.
Oh, I see what you're saying. It still shows. Okay, that's great.
It
I didn't
still
notice
shows,
that.
yeah.
Okay, that's okay.
Well, it shows.
It shows for me.
To some
Yeah,
extent.
depends on the angle.
It's okay. I don't need that.
It's not a universal property.
Right. So now I'll tell you one kind of proposed answer or partial answer is this topological entanglement entropy. Which was introduced in these two papers. So there's what's Pascal. And there's our paper. Spell my name. So, okay, so topological entanglement entropy is not going to give you the full TQFT, but it's going to give you some information about your anions and your TQFT from the ground state. And so how does it work? So it's going to be in terms of the ground state density matrix. So let rho be the ground state density matrix. And I'm going to think of it on an infinite plane, because I kind of want to be able to take my regions to be arbitrarily large. I mean, you can think of it as just a density matrix on some patch, some very large patch. But since we want to take a thermodynamic limit, at some level I kind of need an infinite plane. Okay, so given this ground state density matrix, I'll show you how you can, or can give you a claimed way to compute something about the TQFT. So how does it work? So what you do is you consider the following geometry. So we're going to take a big annulus. And I'm not going to draw, but there's some fine-grained lattice underneath this. So there's a big, huge plane of lattice here. And we're going to take this annulus region, and then we're going to divide up into these subregions, which I'll call A, C, B, and B. Okay? And now, given this annulus in these four regions, I'm going to take a particular combination of entanglement entropies.
B or D?
Sorry?
Is it BB?
You wrote B.
Yes, yes. Sorry, I should have emphasized that. So A and C and then B denotes the union of these two.
Okay.
Okay. So I'm going to define gamma, which is going to be this topological entanglement entropy. It's going to be, there's a factor of 1/2, which is just a convention of S, and I'll define what all this means, but this is the entanglement entropy of region AB plus the entanglement entropy of region BC minus the entanglement entropy of region B minus the entanglement entropy of ABC, of region ABC. Okay, and this is called the topological entanglement entropy. And by the way, this definition, I'm using a very specific definition, which turns out to be important. I'm using a specific definition of the topological entanglement entropy from our paper. There's another definition you can have from Cuskel's paper I'll comment on at the end of the talk. Yeah?
I wasn't fast enough to follow your previous answer. In which sense are the two regions B the same?
B denotes the union of those two regions. So A is this region, B is the union of these two, and C is this region.
Okay.
So just notation. I could call that B1 and B2, but then I would just have, when I write BC, BC means B union C. Sorry, BC means B union C. So it's B, B, and C together. So it's this well, 3/4 of a circle, right? Yeah. AB denotes this 3/4 of a circle. Actually, it doesn't matter if these are perfect quarters, but roughly speaking, AB is the left 3/4, BC is the right 3/4, B is top and bottom, and ABC is the whole annulus.
And the lattice extends over the whole plane.
Sorry, the lattice extends over the whole plane, and I could draw, but I'm afraid it's going to make it hard for me to see this. But yeah, there's a lattice out here, and there's even a lattice in here, and there's even a lattice in regions B and C, but I don't want to draw it because it's going to be hard to read. Okay, so does that make sense? So you have a whole lattice, and then you're going to look at these regions, and now let me just define some notation here. What do I mean by these rows? So when I write rho sub R, this is just the reduced density matrix, right? So this is just trace of rho. You take the full density matrix on the whole lattice, and you trace out R complement. So this is the reduced density matrix on region R. And when I write S of rho of R, this is the von Neumann entropy of that reduced density matrix. So it's minus trace of rho log rho. Okay, so, and I think the one thing I wasn't clear about is when I say AB, it's A union B. So this means take the reduced density matrix of this left 3/4, compute its von Neumann entropy or equivalent. That's, you would commonly call that the entanglement entropy of region AB. This is take the von Neumann entropy of, or the entanglement entropy of the right 3/4 of the annulus. This is take the von Neumann entropy of the top and bottom, and this is take the von Neumann entropy of the whole annulus. Okay, and then so it's a combination of entanglement entropies. Okay, and the idea is this particular combination of entanglement entropies has some interesting information. You get some constant gamma, and the limit that the regions are very large, this gamma is supposed to tell you something interesting. I'll tell you what's supposed to be. It's supposed to tell you something about the anions. Yeah.
So I think it's clearly arranged so that all the divergences from the
That's
edges are cancelling.
Yeah. So
But
we'll
even
talk
if you
about
just took one circle, we know that the divergence is just perimeter. So you can just subtract it, I guess, on the lattice, and you get S0,
Well, the question is how you can. So I'll talk about that, but it's unclear. So there's a couple issues. One is this particular combination has some very nice properties. It's the conditional mutual information.
Yeah.
That's going to be very important for what I'm going to say. In fact, okay, we'll get to that. But also maybe I can comment on what you're saying in a few minutes when I talk about this point of view that you're discussing, which is there's another point of view on gamma as it's the constant correction to the area law.
Yes.
Let me get to that. Maybe I'll come back to your question when I get to that. Okay?
Which is
The short answer is that to define that constant correction of lattice it's not really clear how to define that in general.
But
so you have to do some subtraction scheme. And actually, so you could say, oh, any subtraction scheme is equally good.
Yeah.
That may be true, but I'm not sure of that actually. So in fact, some subtraction schemes have different properties from others. So this one is conditional mutual information. So that's going to be key to everything I'm going to say about it.
So from the continuum, we expect that at least the first observable that I mentioned, just one disk, would be just S0, 0. The S matrix, the 0, 0 component of the S matrix of the
That's
anions.
right.
So is the gamma the same?
Yes.
Okay.
In fact, yes, exactly. Well, it's supposed to be. It won't always be. Yes.
Is the density matrix well defined in the limit of these regions into infinity?
So what you do is, the idea is, again, this is just a claim, so we're not proving anything here, but the claim is take some large regions, compute this, you'll get some number. Then take larger regions, compute it, you get some number. And the hope is that it's going to, the limit will be well defined, the limit for gamma. So you first compute this for finite regions, you get the gamma for a finite region, and then you take larger and larger regions. It's just like if you're doing long-range correlations or something, compute it for a finite distance, and then take the limit that the distance gets longer and longer and longer, the separation. So this is the topological entanglement tree. Now, yeah, as I was saying, this can equivalently be written as quantity in quantum information. It's an important quantity in quantum information known as the conditional mutual information. So equivalently, gamma is equal to 1/2 of something. This is just, I'll write down. This is just some notation. This is called conditional mutual information, quantum conditional mutual information. So that's just a word for this particular combination. So whenever you have any three sets, they don't have to be in this geometry, but if you have any three sets of sub-regions, A, B, and C, of some system, and you compute reduced density matrices and you compute this combination, that's a quantity which is important in quantum information. It's called a quantum conditional mutual information for those three regions. And so that's just synonymous with this combination. That's all I'm trying to say. Okay, so basically the topological entanglement entropy is the quantum conditional mutual information of these three regions in this particular geometry.
What does the notation C/B mean?
So it's this mutual information between A and C given B.
Oh, I see. Okay, thanks.
But that's what I'm going to get to now, which is what is the meaning of this combination? So the way I like to think about it is this combination kind of measures correlations between regions A, B, and C that are global. They're correlations between A and C that don't come from local, so-called local correlations involving only A and B or only B and C. So this measures, at least intuitively, I think of this as measuring global correlations. In ABC, i.e. those that don't follow from kind of local correlations.
So in the continuum language, is this the same as saying UV divergences somehow cancel?
I don't think so. So as I said, there are other subtraction schemes, like in Kataev and Preskill, there's another subtraction scheme, which I'll mention at the end, which is not the same as this. It's not related to quantum conditional mutual information. And on the bound that I'm going to prove, we don't know if it holds for that.
Okay, so let me rephrase it. It's the same as saying UV divergences cancel, but I still have some information about global properties.
Well, this statement here I'm making is a very specific statement that's not about canceling of. Are you asking me about this statement?
But you could imagine some entropy which has divergences but also has global information. So you want to get rid of the divergences but keep some global information. Is that the logic?
Well, roughly speaking, right, except the divergences don't enter into this calculation at all, because I'm thinking on the lattice, so there are no divergences.
I understand, but when you say local, you probably mean effects of the size of the lattice, right? This is what you mean by local, or is
yeah, you could say that. Yeah, so maybe you could say in that sense it's related to divergences. But let me be specific about what I mean by this. Is the way I like to think about this is, let's imagine that you start with a density matrix. It's not really a ground state density matrix. Imagine starting with an infinite temperature density matrix. Okay, so it's a perfect mixed state of all possible combinations, right? So if you took such a state, it's clear this combination would be zero, because all of these density matrices are just perfect, complete mixed states, pure, perfectly mixed states on the three regions. All these von Neumann entropies are just going to be log 2 times the number of spins, let's say, in each region. Everything will cancel. Okay, so that's if it's a perfectly mixed. Now we can imagine introducing correlations. We start from this mixed state and we start to modify it, add some correlations. And we can ask, when will this quantity detect those correlations? So if I add some correlation that's just in region A, nothing's going to matter, because sure, that's going to reduce the entanglement entropy of region AB, or that it's going to reduce the entropy of region AB, right? Because I'm going to have fewer states, all these fewer states are going to appear in this mixed state because I have some correlations, but it's also going to reduce ABC the same amount. So if I introduce some correlations just within region A, nothing happens. Similarly, if it's just within B, just within C, and even within regions A and B together, again, some correlation between A and B will reduce this entropy, but reduce this the same amount. On the other hand, if I introduce a global correlation that involves all three regions, right, that global correlation won't be detected in any of these three terms, but it will be here. So if I introduce some global correlation, this will go down, and then this quantity here will become positive. Okay, so that's at least the intuition here. A global correlation between A and C will reduce this term without affecting the other three, and therefore lead to a gamma, a finite gamma. And so gamma can be thought of as detecting such global correlations. And that was certainly the motivation when we wrote this down. At least my motivation writing this down was to try to detect a global correlation involving all three regions. Now, why would we want to detect a global correlation?
Sorry, question.
Yeah.
Is it useful to think of this as some finite difference second derivative of S of rho on the space of subsets R?
Finite difference.
I mean, this looks like a finite difference, second derivative finite difference, except that you're working on sets, and you're adding sets.
Yeah,
function of this variable, and you define a second.
Right, I know what you mean. Yeah, I don't know how to think of it that way. Maybe that's an interesting. Yeah, maybe something.
Your previous argument basically, I think, says that you cannot change this quantity locally, right?
Well, what I was thinking is a hand-waving argument. It's a hand-waving argument, but the hand-waving argument is, introducing local correlations between regions A and B, even if it's like actually pretty global in this picture, like even if it spans this entire 3/4, it's going to affect this term and this term the same amount and won't have no effect. And similarly, a local correlation on BC will have no effect. But if I add some kind of global correlation around the whole annulus, that will only affect this term and therefore will show up.
But can it be proven that by changing the state locally, this quantity is just...
Excellent question. Okay? So what you're asking is this an invariant under, one way of saying is this an invariant under finite depth local, finite depth quantum circuits? And the answer is no, it's not. That's part of the difficulty that we have to fix. So I'll get to that, I mean, that hope was, I think when we wrote it down, if you had asked me at the time, I would have said yes, it's probably an invariant. I didn't think it through carefully, but I think I would have said yes. But now we know that's not true. Yeah,
So if you had a system with
but that was certainly the hope. Yeah.
long-range correlations, like a gapless system, would gamma still be well-defined, or would you expect?
Yeah, gapless system, I'm not sure. It probably might depend on the geometry. Like like here I said it's an annulus, but the idea is this won't matter. Like it doesn't matter if it's you can stretch. You know, it doesn't have to be a perfect annulus. It's just topologically.
But in the
But if it was a gapless system, then the details would matter. The like ratios of distances would matter, and so on.
But in the continuum, people believe that the answer is yes.
Really?
Yeah.
It doesn't depend on like.
Yeah, because all the divergences cancel.
No, but I mean, wouldn't it matter whether?
No, the answer would depend on the shape.
Yeah. Okay.
But the quantity will be free of scheme-dependent
Okay.
issues.
Yeah. Yeah, I think what I meant is it depends on the shape. Yeah.
This might be premature, but why do we exactly require an annulus? Like, why is the middle region sort of empty and not just?
Well, because that's the maybe let me tell you what I'm going to say next, and then you'll see why at least why we thought of using annulus.
Can you also define this quantity using the Rene?
You can, and people have done that. The bounds I'm going to discuss we only know them for the von Neumann. Because the conditional mutual information is kind of only nicely behaved. There's no really, the Rene version of this doesn't have the nice properties.
So you need to use the strong subadditivity.
Yeah, in fact, the argument, this bound that I'm going to talk about follows only from strong subadditivity, plus some simple assumptions about anyons. Okay, so now what's the intuition and motivation for thinking about this annulus, or thinking about this quantity? So the idea is that states with anion excitations actually do have such global correlations. Okay. They have these kind of global correlations, and let me show you why. So let's draw the picture again. So suppose I draw my picture here. So when you have a system with anyons, you always have what we would call string-like correlations, or if you're more field theoretic, you might call it Wilson line-like correlations. So whenever you have an anion system, you can always create a pair of anyons, by some local operator, and then you can move them around, and you can take, let's say, so I create like an A and an A bar. It's like the anion and the anti-anion with some local operator, and then I can move A, let's say A or A bar around, and then I can, annihilate them, with each other. And so that gives you like a string-like operator. It's an operator supported on a string, and by construction, this string-like operator takes your ground state to the ground state, right? Because I created the excitations, I moved them, and then I annihilated them. So this is what we call a string-like operator, or you might call a Wilson line operator. And in any anion system, you always have these kinds of Wilson line operators, and they always have some fixed eigenvalue, right? Because that just depends on the normalization. But they take the ground state back to itself. So you can think of this as a global correlation. What is it measuring? What's the correlation? It's measuring whether there's an anion in the center, right? And so in the ground state, there's no anion in the center. So there's kind of a string-like correlation in any anion system, which is coming from the extra information that you have, which is that there's no anion in the center. So in this picture here, there's always some kind of string-like correlation I can draw like this, which involves all three regions, okay? I'll call these operators W sub A, W for me, Wilson. For every anion type, there's this corresponding anion string operator or Wilson line operator, and that operator is some kind of global correlation, and it involves all three regions. And it doesn't come from some local correlation. It's not a product. You can't take this, crucially, you can't take this operator and break it, right? If you break it into like half an operator, the ground state is no longer an eigenstate of that, right? It's only the whole string operator, which the ground state is an eigenstate. It's only the whole string operator which has a nice value.
So the open string is an excitation.
Exactly. So there's a global correlation involving all these spins, and it's coming from these string operators. And so the idea is that when you look at this combination, this particular combination, or at least our idea was we will be able to detect the presence of these string operators. these string-like correlations. So we would expect that in any anion system, because you have these string operators, you're always going to get a positive gamma. That was our intuition. Okay? You must get gamma positive if there are anions, because you have to. And the whole idea was this is designed to detect these string-like correlations. Since the string-like correlations are there, you're going to get it. Now here's the weaker part of our argument. So this is kind of, I think, is pretty clear. Well, intuitively makes a lot of sense. You should have positive gamma if there are anions. But then we had the other idea, which was that if you don't have anions, well, you know, there's this. Your intuition is the ground state just has kind of local correlations, and so then this thing should just be zero. So that we sort of thought in contrast. We expect gamma to be zero if there are no anions. Because there's no reason for this kind of global correlation. Right? These kind of string-like correlations only happen if you have anions. Okay? So there's sort of no reason for correlations. Or global correlations. Okay, and so based on that, we have the intuition that gamma should be greater than zero for anion theories and zero PTQFT ones. And so that's the intuition, and then hopefully that answers your question why you use an annulus, because you're trying to detect string off. Okay, so now let me take that specific quantitative claim. So this is like some intuition, gamma should be greater than zero if there are anions and zero if there aren't. There's a more specific claim that was made about the TE, which is more quantitative. It says that gamma should take a particular value. Okay, so the original claim was in the limit of very large regions, gamma should take the specific value, it should be, which is given by log of d. D is the total quantum dimension. So let me define it and then I'll explain what it is. This thing is called the total quantum dimension. Total quantum dimension of the anion of the TQFT. Okay, and I'll explain what this means in a second. But roughly speaking, this quantity here measures how many anions you have. It's how many anions you have. This is the sum. This is the sum over all the different anion types. So in general, you have more than one type of anion. So it's the sum over anion types weighted by the quantum dimension. Quantum dimension. This is the quantum dimension. The details of the quantum dimension aren't going to be super important here, but the quantum dimension measures roughly how non-abelian your anion is. So if you have an abelian anion, dA is just 1. If you have a non-abelian anion, dA is greater than 1. So roughly speaking, this is measuring how many anions you have, with non-abelian anions counting for a little bit more. You take, and so D is measuring that. So the idea is that the more anions you have, the more non-abelian your anions are, the bigger D is, the bigger gamma will be. So that was the specific claim. And actually, let me just write over here the details of these quantum dimensions.
So if you take your space to be just, if you divide your space into two halves, you cannot actually do this construction?
Two halves.
Two halves, like A and B. And you
mean like a single bipartition, yeah.
Yes. So you still cannot actually make sense of gamma in this case?
Well, I'll comment on that in a moment. I think that's related to what Zohar was saying. So there is a way of thinking about gamma in terms of a single bipartition, but it's not clear how to make it precise on the lattice.
I see.
Maybe I'll get to that in a second.
So is this D is roughly how many Wilson lines I have?
Roughly, yes. So let me just, for an abelian theory, that's literally what it is. So that's what's going to sit here. For an abelian theory, all these D's are 1. So this just counts how many anions you have. It's the square root of the number of anion types. For non-abelian theory, it's not that. It's square root of the number of anion types, but weighted by this. So just to put right down on the board, 2 comments just to understand about D that I think are going to be important. The only things you have to know about D is, first thing you need to know is when we talk about anion types, we always include the trivial anion, which is like the unanion. It's just the vacuum, the no excitation at all. And so that we call that anion labeled by 1. Okay? And the trivial anion has a D which is 1. So that's an important special case. So D of 1 is 1. Okay, this is the trivial anion. And a theory without any anions at all, we would say has a single anion, the 1 anion. Okay? So a boring state would have a single anion which would be labeled by 1 and would have D1 equals 1. So that's one thing you should know, that the trivial anion has a quantum dimension of 1, and more generally, abelian anions also have 1. Okay, those are the only one. I think those are the only things you need to know to understand what I'm going to say. Okay, and so so what this means in particular is that if you have, so in particular, just to connect it up with the intuition I said over there, if you have a theory without any non-trivial anions, suppose you have no non-trivial anions. If you have no non-trivial anions, then this sum will only have a single element in it, A equals 1. And D1 is equal to 1, so the capital D will be 1. And then the log of D will be 0. Okay, so this is consistent with kind of what we were saying here. There are no anions, gamma should be 0. On the other hand, if you do have some anions, then you're going to have at least one, you're going to have at least 2 elements in this sum, right? So you actually, so in particular, D has got to be greater than 1. In fact, it has to be at least 2, but I won't emphasize that here. It's got to be greater than 1 because they'll have the trivial anion plus something else, and so gamma will be greater than 0. Okay, so it's like the quantitative claim, and that's kind of the intuitive claim over there, or the intuition that motivated this. Okay, so and this formula here that was claimed in both those papers, there's been a lot of examples we've calculated gamma, and it seems to work in many examples, many exactly solvable models, even in non-exactly solvable numerical calculations. Many cases, people have actually taken lattice models and computed the gamma, and it seems to give you exactly this value log D.
Michael, can you say why? Sorry.
Yeah, this one.
Why did you say that D is bigger than 2? In U1 level 2, D is square root
No,
of
greater
2.
than or equal to 2. Sorry, D is, sorry, I didn't mean 2. You're right, the square root of 2. Yeah, I sometimes forget the square root. Yeah, the thing inside the square root is 2.
So this is a conjecture.
What is?
This formula?
Yeah, this is a conjecture, and in fact won't be quite correct.
Yes, but okay, what is the logic behind it?
Oh, so where did this come from?
Yes.
So I'm not going to give the derivation of this. I was trying to give you some intuition over there. But I can just tell you how it was derived. So in our paper, we basically just calculated for a large class of exactly solvable models, and we got this formula, and we just so we conjecture it just holds. In the Kitaev-Crespo paper, they calculated from TQFT.
In the continuum, it's
In the continuum.
obvious, yeah. If you assume that the continuum logic works, it's obvious that it should be true.
Okay, so yeah, that's the formula, and then I just wanted to comment on this. There have been several questions about how you define gamma in terms of a single bipartition. So let me just mention that. So I think of this as a heuristic definition. So there's an alternative heuristic definition of TE, which I should mention. This alternative heuristic definition is you do the following. You just take a single region, A. Okay, and again, there's some lattice here. And then you look at the entanglement entropy of that single region, and you say, okay, I expect that's going to follow some area law. So they'll be proportional to dA is supposed to be the length of the boundary of A. Okay, there'll be some constant here, right? So this is the area law term. And the idea is that typically when you calculate this, you'll find there's an area law term, but there may be a constant correction, which is gamma. Okay, so gamma is a constant correction. And then there may be some other terms which go to 0 in the limit of longer and longer boundaries. Okay, so the heuristic definition is the way you calculate the TEE is you just look at the entanglement entropy of some large region. You'll find some part of it that's scaling with the length of the perimeter, and then you look at the constant correction. And you can see the, I guess I erased it, but you can, oh no, it's over here. You can see that the consistency between these two formulas, because if you say you assume that this is true, if you plug it in here to our formula, which was S of rho AB plus S of rho BC plus S of rho B plus S of rho ABC. If you plug it in there, you can see what's going to happen. Is, as I think Zohar and other people are saying, is this area law piece is going to cancel out because all those lengths cancel out in the sum, and then the constant pieces. Sorry, we had a 1/2 out front. That's important. So gamma is equal to this, right? So the constant piece, you can see you're going to get a minus gamma here, because you can get a minus gamma here. You're going to get a minus 2 gamma here, because B is made up of 2 regions. So it's going to give you get a minus gamma, minus 2 gamma. And then you're going to get also minus 2 gamma here, because this has 2 boundaries, right? And so then when you do it minus gamma plus minus gamma minus 2 gamma minus 2 gamma, you get exactly 2 gamma. You divide by 2, So, so one way to think about it, if you like this heuristic definition, is you could say, okay, this definition I wrote here was just some way to cancel out all the area terms and extract gamma. Okay, so that's one point of view.
A very naive question. Sorry.
Yeah.
You keep mentioning area law, but then you also said that it's the length of the perimeter.
Oh yeah, so people,
So
that's right.
Why
That's just a terminology. People use the word area law because originally people were thinking about partitions in 3 dimensions. So area is area of the boundary, but in 2 dimensions, area is a length. It's terrible, but it's just, we have to deal with that. When people talk about area law,
Okay, I'm okay with this.
yeah,
Okay.
they never heard anyone say length law. Maybe perimeter law.
Perimeter law.
I know, but maybe we could say that. Yeah.
So you have 2 radii for your annulus, right? So
Yeah.
when you're talking about large regions, you always imagine sending
Both.
both with the ratio.
All length scales should get large. It doesn't matter what the ratio is.
Doesn't matter.
And it doesn't matter that it's an annulus. So
Basically,
that was the thing. It wouldn't matter. None of those things should matter. And in practice, it seems in many cases it doesn't matter. But I'm going to show you that, that conjecture isn't quite correct, the one that was written there. And so in that sense,
But I mean, should I be thinking like actually, I could take a limit so that they come together.
It doesn't
It's
matter.
Like a tiny.
it doesn't matter. So the
line, almost like a line.
the original picture, which I think is probably morally correct, is that as long as all length scales are divided, go to infinity, it doesn't matter what the ratio is.
that's because you're ignoring these dots. This is why you need all length scales. Right? They will be suppressed as 1 over.
Yeah.
And that's why you need all length scales. So you tune this so that the first term cancels. And once you've canceled the first term, all the
Well,
other
that's
terms.
you're saying why it needs to be big. That's one way
Yes,
to say
exactly.
it. Yeah.
That's why.
I mean, again,
But the ratios don't matter.
that's
Because-
right. The ratios don't matter.
Because ratios don't show there.
Right. So anyway, from this picture, you can think of this ACB direction. You can think of the quantum conditional mutual information as just a subtraction scheme. Yeah, go ahead.
Yeah, exactly. From this point of view, you can extract gamma just by subtracting.
But on a lattice, I don't think that's well defined. How do you talk about the length of a boundary? Doesn't make sense.
Because of angles, or?
Yeah, exactly. The corners. I mean, how do you?
Well, but there is a cusp function at the corner, and you can subtract them systematically.
I mean, I don't think so. Not on a lattice. There's like.
It's like when people measure the cusp anomalous dimension on the lattice. So
Well,
they
for-
know how to subtract this 90-degree
I mean, you're
cusp.
thinking about like critical theories or something, but there will be corrections that, I don't know. I don't know how to make sense of this definition when you have corners in practice on the lattice. I don't know. maybe you
But
can
corners
explain that.
introduce a universal cusp function. So if we know that, we know how to subtract
What
corners.
does that mean, universal? I mean, for a particular, there'll be some, it'll depend in detail on what the correlations are right near that corner. I think you're thinking in some, I don't know, some field theory context. Yeah, go ahead.
If you're in the cylinder and you have translation invariant.
Yeah, that's the one case where people have used this, and it kind of makes sense. But even there, my personal view is, well, as I'm going to say, the bound that we're going to prove, I don't know. I'm not as confident about this formula, even on a cylinder, as this.
I know you're going to the kind of issues that they're going to talk about. I mean, they seem equally applicable to both.
What does?
These issues about kind of additional degeneracies.
Yeah, but I'm going to show that there's an inequality. There's an inequality that gamma holds, that is obeyed by gamma, but that inequality you can only prove it for this conditional mutual information. I'm not sure it necessarily holds. I don't have a counterexample yet to the inequality on a cylinder, but there might be one.
Are there cases when we know that kind of we get other problems with the cylinder?
Oh, beyond? I don't know. I have to think about it. Yeah, I think. Yeah, I have to think about it. I think in general the cylinder. Yeah, maybe we can talk about it afterwards. Okay. There are difficulties when you're not working with a local patch, even defining. Yeah, go ahead.
So I understand you've mentioned many times the importance of this particular setup, so I appreciate it. And just can you give us a sense of your original intuition for why it's important that B has both the top and bottom region? Suppose B doesn't have the bottom region, that A, B, C all touch.
Oh,
Is
then
that
it
intuition
wouldn't.
or
If A, B, C all touched, then this would definitely be.
okay. So that level.
Let's see what would happen there. Yeah, this would be non-zero even for local correlations, because when I said because this quantity, like if I had a correlation between A and C, imagine I had a direct correlation between A and C, that would also show up here. Like a correlation between a spin here and a spin here, that would show up in this formula, right? Because that would influence this term but have no impact on these terms. And if A, B, and C were touching, then I would always have those correlations between A and C. See what I'm saying? You draw your picture. I think you're thinking like this.
I see.
Right? I would have those correlations. So you need them to be sort of separated to, yeah.
Do you know if this gamma is a quantity that's monotonic under RG flows and gapless theories, or maybe someone else?
I think for like a circle it is, right? You were talking about when people talk about it.
Yeah, pick a shape.
It might be, but someone else can comment on that.
So that kind of gives it a definition outside of gap systems and constrains what gaps PTQFT could get. From
right, yeah, if you, that's true. So if you, I guess the question though again is whether the circle definition again doesn't quite make sense on a lattice. But I hear what you're saying. He was saying that if Luca was saying if you deal with a circle, if you think about a continuum field theory and you take a which is in a circle, which is kind of the perfect geometry for using this definition, then this constant gamma maybe is reasonably well defined in that case. It's not just a circle, and that quantity even has some nice properties, some kind of monotonicity and other properties that improve it. And so he's saying that could be interesting. That can give you some constraints.
I thought this doesn't depend on the shape. Why do you say circle?
I think it does.
Well, I think it probably. I mean, you have to be worried. Like this is very heuristic, right? There's probably going to be some dependence on the curvature. Yeah.
But quantum Hall systems, which are defined in the continuum, I mean, their station.
Yeah, people. In fact, people have used this in quantum Hall context, and it's more common to use this actually in numerics than to use the subtraction schemes.
So what's the problem on the Senida with translation symmetry on one direction?
Well, I just don't know whether I don't know. I don't have a specific problem, but I'd say there's 2 points. One is that I'm going to show you that this quantity has some nice properties. The results I'm going to prove about this quantity, I don't know if they hold for this quantity. That's what we're saying.
But it's well defined on the Senida.
It's well defined, but it's not clear it's universal. Well, I'm sure it's not universal.
Yeah, that's my paper.
But the point is here I can prove something that's sort of an inequality that's universal. But I don't know if that holds on a cylinder. Maybe there are other questions. All right. Let me just see where I am, whether definitely behind where I want to be, but I know people are probably tired, so I don't know if we should take a break. What do you think?
5 minutes is fine
Okay.
if you're in a hurry.
Okay, you want to take a 5-minute break?
Yeah, just let people maybe use.
Yeah. Yeah, why don't we take a 5-minute break?
Yeah, 5 minutes. Sharp.
more amenable.
How is it to work with you?
technique.
Oh,
Down
So
to
then
me.
you can do
it's
a general
fantastic
KK
actually.
reduction.
We are
And you can ask how is the non-zero reduced by the
yeah,
one
we're
plus one
doing some cool
dimensional
stuff
theory.
actually.
He told me.
And then you can
Oh,
do
he told you?
convolutional
Well, not the details, but
we
generally.
see how much interaction
Yeah.
among the lowest modes to reproduce the full HDL.
The non-trivial thing is that we have some like preliminary results, and he agrees that they are non-trivial, and that's convincing
That's good.
Shigeki
And then you
that
can go back
something
to
is
the
non-trivial is already highly non-trivial. So
Yeah.
I'm proud of that achievement.
Ah, that's good.
So that was kind of the first half of what I was going to say was, so far, was just sort of what was the original proposal about the topological entanglement entropy, the lattice definition, this kind of continuum picture. Now what I want to talk about is why some issues with this original proposal. And so I'll start off by talking about this Bravi's example or counter example. This is due to Sergei Bravi. It's described in this paper. So how does this example work? It's going to be an example where basically gamma is non-zero, but there are no anyons. Okay, so it's a system that has no anyons. There's no question it has no anyons. But the topological entanglement entropy is non-zero, and it really doesn't even matter what definition you use. It's non-zero with all these definitions, including this definition. Okay, so how does the example work? So it's actually a 1D example. So let me draw a picture of it. Bear with me. It may seem strange that it's 1D when everything in this talk has been about 2D, but hopefully I'll be able to explain that to you. So we have like a 1D chain spins. These are each spin 1/2 spins. And I'm going to sort of, some of the spins are going to, it's going to kind of, I'm going to draw it as 2 chains actually. Okay. So you could think of it as 1 chain or 2 chains, maybe it's up to you. And so it's going to be a model defined on these spins, and I'm going to number these spins like this. 1, 2, 3, 4, 5, 6, etc. All the way up to, let's say, spin n. N is even. Okay, so it's 2 n spins. And the Hamiltonian looks like this. So let psi be the unique ground state of the following Hamiltonian. It's basically the cluster Hamiltonian, the cluster state Hamiltonian. Okay, so this is the Hamiltonian that, if I were to draw it here, it does something like ZXZ. You know, ZXZ. I don't want to draw it because it's going to mess up my picture, but ZXZ on 3 neighboring spins, right? And because the numbering works this way, it would be like ZXZ on these 3 spins, ZXZ on these 3 spins. You should think of this as a zigzag chain, the way I worked it, right? Is that clear? Okay. So
when you think of it as 2 chains, it looks like.
The reason I called it, you mean, why did you say what?
Why did you draw it as 2 chains?
Because I'm going to draw a cut in between the 2 of them.
You're going to draw.
The partition is going to. Let me draw the partition. Yeah.
Okay.
I could have just drew it as 1 chain, but then I'd have to draw one. Yeah. It's just going to. You'll see. So it is 1 chain, but I've drawn it this way. Okay. Just makes my picture easier. So the idea is, okay, let's take this system and let's just let's imagine we just try to calculate this. We thought of this as a 2D lattice model, and you could think of this as a 2D lattice model. What you could do is you could put all the spins. Imagine I have some lattice of spins. In the interior, I put all the spins in some product state. They're all pointing up. And exterior, they're all pointing up. And then just along this little disk-like region, they're doing something a little more interesting. Okay? And then and suppose my friend hands me that as my wave function, right? So the wave function is some boring product state in the interior. I'm not even going to draw it. Some boring product state in the exterior, and then has this state right on this circle. And then suppose I get unlucky enough that I draw my regions like this. Okay, and I do some cut. I don't know, it doesn't matter that much, but I'm just. Okay, so this is going to be my region A, this is B, this is B, and this is C. Okay? And suppose I were to do that, right? I take this, inert, they don't matter at all in terms of entanglement entropy. So I can just calculate it just for this one new state and see what do I get? Do I get what quantity do I get here for gamma? Oh, by the way, this state here is called a cluster state. And it should be clear that there are no anyons in this system. In fact, this state that I've written down, this cluster state, as a 1D state, you can relate it to a product state by a finite depth circuit. There's some finite depth circuit, collection of local unitary gates that will transform the ground state psi into a product state. So this is, morally, this is just a product state with some local correlations. And in the interior, it's like completely a product state. I mean, I didn't even draw it. You know, we have lots of spins in here, you know, lots of spins that are completely in a product state everywhere. So it's a product state everywhere except right around this cut, and it's almost a product state. It's a product state up to some local.
So when you say this state, you mean the state which is the ground state of that homogeneous?
Yes. Okay, so there's certainly no anyons because it's basically a product state everywhere except along this 1D chain, and there it's equivalent to a product state up to a local unitary. However, gamma, if you calculate gamma, you get 1/2, you get something non-zero, in particular you get 1/2 log 2. Okay. So this is already, this is a problem. Because we have a state which has absolutely no anyons under any definition, but if you calculate gamma, and actually you don't have to calculate this way, you could also calculate this way. However you want to calculate it, you would get this finite value, 1/2 log 2. So let me try to explain where this is coming from, right? This is, I tried to argue last time that this shouldn't happen. When you don't have anyons, there's no reason to have a global correlation. What happens is this weird state with this particular cut does have a global correlation. It's a global correlation that doesn't come from anyons. It comes from,
but if you push the contours at infinity, then you go back to 0.
Well, that's right.
You
that's
have to
right.
turn the Hamiltonian to keep on following you.
So if you don't like that, yeah, good. So when I first saw this example, and I didn't think it was quite as disturbing as it was, because I thought, oh, this is weird. Like I want to take a thermodynamic limit, but you can modify this example. I don't want to spend time on that. To do a 2D translationally invariant, you can take a cluster state on a 2D lattice, and you can show that there exist weird cuts you can take, arbitrarily large regions. But if you choose your cuts in a bad way, you will still get, in fact, exactly the same physics as this example, and you'll still get this gamma. So I guess you'll have to just trust me that although this doesn't quite look like a 2D translationally invariant system, the physics of this is completely equivalent to a 2D translation invariant system. Okay, for weird cuts. It is true that it's cut dependent, so if you have to choose your cuts in a bad way, kind of an unusual way to get this gamma. Okay, but nevertheless, that's still disturbing, right?
So maybe you could say that this system doesn't have a continuum limit.
I mean, but okay, so we're not interested, but our point of view is we're interested in studying lattice models, right? So what we want to say is, the original claim was, if you have regions that are arbitrarily large, and you calculate gamma, you'll get a well-defined limit, and it will give you log d. And the answer, again, here what you can say is, it's not a well-defined limit, because it depends on which cuts you take. And for some cuts, you get something that's, well, not even close to log d.
I mean, naively, it does have a continuum limit. It's an SPT, and the ground state should be some invertible TQFT. And here, the invertible TQFT will just be like A cup B, where A and B are both Z2 cosegons.
Maybe he's referring to the 2D translation invariant. I think he's probably referring to the statement I made, which is that it depends on the cut you take when you do it on a 2D lattice.
Yeah.
Okay, but let me just explain why does this give you a non-zero gamma? And the reason is, you can see it pretty easily. It's because there's a global correlation. And what is this global correlation? Where does it come from? So basically, you can see it very easily because this is a so-called stabilizer Hamiltonian. It's a sum of, well, it doesn't matter, it's stabilizer. The important thing is just all these terms in the Hamiltonian, they all commute with each other. Okay? That's easy to check. The ZX terms, they all commute. So the ground state is an eigenstate with eigenvalue 1 of each of these terms. So in particular, so Z I minus 1, Xi, Zi plus 1 times psi equals psi. Okay, so that's this even defines the ground state. The ground state is the unique state that obeys these properties. So the ground state has these kinds of local correlations. But if you take a product of those local correlations, let me draw a picture here. So I'm just going to zoom in on part of the boundary. this will have eigenvalue 1 under, let's say, this operator, zxz. Right? If I apply this operator to the ground state, I get 1. But that's also true if I apply this operator over here. Right? And also over here. And also over here, zxz. And also over here. Sorry, where did I miss one? Here, zxz. So in other words, if you multiply all these zxz's together, you can see it's a telescoping product, right? All the z's cancel, right? And so what you find, if you multiply these together, you have to multiply the ones where I is odd. So that's what I've drawn here. zxz times zxz times zxz times zxz times zxz. You multiply them all together, all the z's cancel, and you conclude that the product of xi over odd i's on psi equals psi. Right? And so this is exactly the global correlation. It's a global correlation between all the spins. I chose my cut, so those are all on the inside, right? The product of all the sigma x operators, that's what I mean by this notation. This is sigma x, this is sigma z. The product of all the sigma x operators here is equal to 1. In fact, that's the only correlation, it turns out. You can easily check. If you look at the reduced density matrix in region ABC, it's a perfectly mixed state with a single correlation, a single global correlation. So that's where it comes from. This single global correlation, that's going to contribute to this SABC term. It's going to reduce that by log 2 from the value you would get from a perfectly mixed state. And all of these are just the perfectly mixed values. So when they all cancel out, you just get an extra factor of log 2 here divided by 2. And so that's where this comes from. So basically there is a global correlation, but this global correlation is not coming from anyons. It's like an accidental global correlation.
It looks a little bit like since each zxz commutes with the Hamiltonian, also this product of x's commutes, and it looks like it's localized on a codimension 1.
Exactly.
So
it's not a flexible.
It's like maybe a subsystem symmetry.
Yes, people do call it that. That's right.
So if it's a subsystem symmetry, these things don't even apply because like even in the continuum, there are issues with this thing if there is subsystem symmetry. So I wouldn't say it's shocking even from the continuum.
Well, it may not be shocking, but whether it's shocking or not, it still is a problem, right? Because it means that if you want to have some universal way to extract anion data from a lattice, you can't just compute gamma and
maybe you have to impose the condition that there are no codimension 1 charges.
Well, that's not something. How do you know? And it's not clear, by the way, that it has to be subsystem symmetry always. Probably doesn't. That's probably the most natural way it happens, but it could happen from, I don't know.
Is the entanglement spectrum double division?
This one, the entanglement spectrum is completely flat. It's completely flat. All eigenstates appear with eigenvalue, the same eigenvalue. All eigenstates with this product of x equals 1 appear with the same eigenvalue, which is 1 over 2 to the n minus 1. Yeah.
Kind of make a connection between this and the original anion setting. It's a bit as if you have kind of confined or X the anion into a trivial phase, but with matter degrees of freedom, you're somehow leaving the matter degrees of freedom out of the cut. Because it's a bit like the 1D version there, right? Like your X is like it would have been an Ising domain, like a deconfined phase, but it has been condensed by coupling it to the other degrees of freedom, which are like the matter degrees of freedom of this 1D Z to gauge theory. And if you somehow, maybe the general lesson is like if we leave the matter degrees of freedom, even in a trivial phase out of the cut, it can still look like a remembered anionic constant.
There are definitely close connections between this cluster state and, I know exactly what you're saying. The cluster state is kind of related to Higgs phase. You can think of it that way. And there's also close connections to the Tor code. You can think of this also as a really small piece of an annulus of the Tor code. There's different ways of thinking about it. Yeah.
I have trouble understanding why this is like not like a string operator. So if suppose you take the product of sigma x's and then like sandwich it between the z of I minus 1, but I is like the first one, and then z of I plus 1.
Yeah.
That's a string operator, right? Which is
that string operator would look like x, 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 and then would have 2 z's.
Exactly. So that's a string operator. Why
but it's not a flexible string operator. So anions, what's special about anion string operators is you can move them anywhere in space. This string operator is confined to this 1D line. So that you don't just have a string operator. I think maybe what you're saying is if you have a flexible string operator, you really need to have anions. But this isn't a flexible string operator. Yeah.
global correlation, the product of access and events.
That's true, but that doesn't matter because we're only looking at regions ABC. Like that involves the outside. So, yeah.
So this would kind of be like a fractonic thing where like you're only allowed to move it in this one-dimensional circular region and then can't move it anywhere else.
Right. So okay. So this, yeah, you may or may not find this example surprising, and you could say, okay, it's very finely tuned. And actually, that's an important point: is that all examples that people have found to date that have this phenomenon. So this is called spurious. It's been named spurious TE, and so I think coined that name. And they discussed other examples too. It's been called spurious TE because it sort of seems like it's you're getting a contribution to this topological entanglement entropy, which is spurious. It's not related to anyons. All examples of spurious TE to date seem to be finely tuned. They depend on the, if you change the cut a little bit, they disappear. Even if you apply unitaries, local unitaries, it seems like generic local unitaries will also destroy this, at least in the thermodynamic limit. That's something I'll comment on at the end. But nevertheless, whether it's finely tuned or not, it still means that you can't make a simple statement that gamma tells you the anyons, right? That's not quite right.
Couldn't you average over some annualized?
You could try, but yeah, it's hard. How do you make that precise?
Yeah.
I actually think what you should do is average over, and that's sort of what I'm going to say. If you average over unitary, actually not average, you minimize, that's what I'm going to say. If you minimize over unitaries, you scramble it with unitaries near the cut, you always get the right answer. So you have to consider sort of general finite depth unitaries near the boundary. But yeah, maybe averaging would work. I mean, I think in some sense you don't even have to average. You could just, the general belief is this is finely tuned. If that's correct, then all you have to do is just multiply by some random unitaries. Any random unitary will give you the right answer, basically, with probability 1.
Yeah, but doesn't your example imply it's probably generic in the sense of if you imagine the circuit that creates a cluster state, but you can parameterize it continuously, right? Then along that whole path, you'll get a violation that can continuously has a growing gamma, right? Like this gamma is some discrete value, like some log 2/2. But then if we imagine continuously creating a cluster state by a continuous path of unitaries, then along the whole path of a non-zero gamma, right?
That's right.
And then it starts sounding.
But I'm saying if you take any of those states and you you do some small perturbation, you'll go to
drops
0.
straight back to 0.
Yeah. Actually, I think even now that I think about it, I take back what I said. Even along that path, I think it drops straight back to 0. It may depend, because that path is going to break the Z. So this actually is protected by Z2 cross Z2 symmetry on the inside and on the outside. That's one of the cool things that's explained in this paper. But if you break that Z2 cross Z2 symmetry, which you'll have to under that path, then at least the expectation is it goes to 0 in the thermodynamic limit. Yeah.
Okay, thank you.
So I remember in this paper, it's important for us to show to the known that this state is a non-trivial SPT of Z2 cross Z2. But in your argument just now, you didn't use that.
What argument?
Gamma for this example is non-zero.
For this example, you just can compute it.
Okay. Mm-hmm. Yeah,
but it's true, it's protected. Right. They pointed out that if you ask what type of unitaries will stabilize, like if you apply some generic unitaries, this goes to 0. But there exists a subclass of unitaries, finite depth circuits, which will preserve this effect. And those are those that are Z2 cross Z2 symmetric. They proved in their paper that happens. Yeah.
Is there some kind of long, if you look at trace of a row to the end with some local operator insertions, is there some kind of long range order? Or
you think it's related to that you're asking? Or?
Yeah, is there something it's kind of like if you think about this entanglement defect, right? That there's like some long range order of the entanglement defect.
I think there are signatures in this. Yeah, but if you look at multiple copies of your system, you can see some diverging correlation links. That's maybe what you're referring to. But
generally cannot get long range order, right? In the 1D classically, but maybe like some fine-tuned.
Okay, sorry, I should probably move on because I haven't yet stated my result and I only have 20 minutes.
2 hours not that long.
Apparently not. So then, Okay, so this leads to a question, which is, what is the precise relationship between TED and anion data? Okay, and so these examples raise that question, right? So that's our main result, which is there is a precise relationship, a precise and general relationship, which is that in the limit of large regions, and it really doesn't matter what cut you take, but if you just take large enough regions, gamma will always be greater than or equal to log t. Okay, so in other words, gamma gives it up. You can think of it this way: the value that was expected, by various calculations, is actually it's a lower bound to gamma. Or another way of saying it is, gamma is always greater than or equal to that anion value. This is actually, I think, kind of intuitive because I argued here that whenever you have a system with anions, you're going to have certain global correlations. But you can have other things happening on top of it, like accidental correlations. What this thing is saying here is that those accidental correlations, they can just add. They can add to gamma. They can give you more global correlations. But the anion ones always have to be there. That's one way to think about this intuitively. I think it makes a lot of sense. It's that all that can happen is you can have accidental extra correlations. Now, what does this result mean? It means that gamma, I think in practice what this means is if you compute gamma, you get an upper bound to the anion content. And actually, I'll give you some examples in a second. But yeah, it allows you to upper bound anion content very precisely. Now, this fact that you can upper bound anion content, I just want to draw an analogy to something that's probably familiar to you, which is that if you think about spontaneous symmetry breaking, how do we probe spontaneous symmetry breaking? We probe it usually by picking some operator, some order parameter, and looking for long-range correlations. If you use that approach, order parameters, long-range correlations, allow you to upper bound. It's very much analogous. They allow you to upper bound how much unbroken symmetry you have, just the way gamma allows you to upper bound your anion content. So in other words, if you find some order parameter and it has long-range correlations, you can say for sure, certain symmetries have been broken, right? But you can't, if you don't find long-range correlations, you can't say that the symmetry wasn't broken, right? Maybe you chose the wrong order parameter. Maybe it just happened to be exactly 0 because you picked the wrong order parameter, right? And so it's very much analogous to this. If you pick any given order parameter and you try to use it to diagnose what phase you're in, it only allows you to upper bound the amount of unbroken symmetry. It doesn't tell you precisely what symmetry is broken. Similarly, gamma, for any particular choice of cut, only allows you to upper bound the anion content. So I think there's an analogy. In some sense, maybe this is all we should have expected, because even for symmetry breaking, if you try to probe symmetry breaking using order parameters, you can at most get kind of a bound. You can only bound it on one side. You can say this symmetry was broken. You can't say this symmetry was unbroken.
So there's a proof of this? You gave a proof of this?
Of what?
Of this?
Yes, I'm going to try to sketch that proof. So
there's no global correlation which can contribute negatively to gamma. Is that the...
That's right. So in other ways, the spurious TE is always positive, non-negative.
Is there any kind of correlations? Even anions can only contribute positively, no?
Say that again?
I mean, any global correlation seems to be contributing positively to gamma.
That's right. Gamma is one statement. I mean, I didn't say this before, but I'll say this in a second. Gamma, just information theoretically, that conditional least information is always a positive quantity, period. So actually, the simplest case, the case where you have no anions at all, this is obvious, because log D is 0, and we know gamma is greater than or equal to 0. That's the statement of strong subactivity. So yeah, gamma is always positive, but here we proved something stronger than that, right? We proved if you're in a Tor code phase, gamma has to be greater than or equal to, log 2. So just to give you a flavor for what the implications of this are, and then I'll try it very you know, suppose you find gamma equals 0. If you find gamma 0, then according to this inequality, log d must be less than or equal to 0. That is, the only possibility is d is 1. Or you could say d has to be less than or equal to 1. D, of course, is greater or equal to 1 always. So this means you're in the trivial phase, no anions. So you can say definitively, if you find gamma equals 0 for any choice of cuts, as long as they get larger and larger, you can't have any anions. Another example of the kind of statement you can make is, suppose you find gamma equals 1/2 log 2. For arbitrarily large regions. Like that would be the case if we're there. Then you know d is less than or equal to √2. And then there's really actually only, you know there's at most one non-trivial anion. In fact, you know it. There are really only two possibilities. Either no anions or it's U1 level 2. Like there's really only two theories you could have. So basically, this bound tells you once you find a gamma, you can then limit. Actually, you'll have some finite set of. Actually, I don't know if it's necessarily finite. You have some list of theories with that are compatible with that gamma. So that's the kind of conclusion you can draw. Yeah.
If gamma depends on the cuts that you have, this still applies?
Yeah. So you want to, but yeah, that's right. So for any cut, any large cut, you have to have this bolt. Yeah. Okay. So let me see if I can sketch the proof. I think the proof is kind of nice. I'm going to present a different proof from the one from the paper in the archive. This proof that I'm going to present here is unpublished. What's nice about it is it doesn't really use much. It just uses strong subadditivity. And then I will have to make some very simple assumptions about anions. But apart from that, that's all it is. Anions and strong subadditivity.
If the notion of anion well defined, you're limiting gamma by something that you didn't give the definition of.
Well, you'll see, yeah. So in our other proof, if you don't like this proof, in our other proof, we have a proof on the lattice where we basically show that any state, we prove this inequality for any state which is related to an exactly solvable model, basically like a string net model, by a finite depth circuit. And for string net models, we can define what log d is. But this definition, the proof I'm going to give here is not going to rely on that. You'll see whether you find it meaningful.
So the other proof doesn't apply to chiral states?
Well, not directly, although we have a kind of heuristic argument that it should also apply to chiral states. But our rigorous proof doesn't apply to chiral states. Okay, so proof of inequality. So this is sort of an unpublished alternate proof. Okay, so how does it work? So the idea is, I'm actually, for the purposes of this discussion, I'm just going to prove it for the Tor code, okay? I was going to show you how it generalizes, but I don't think I'm going to have time for that. So at best, I will prove it for the Tor code. So I'm going to consider a state rho with the same anion excitations as the Tor code. So the same TQFT, if you like. Okay, so in other words, the anion types for people not familiar with the Tor code has 4 anion types. The trivial type, the charge, the flux. It's like a Z2 charge, a Z2 flux, and they're composite. Okay? And they all have quantum dimension 1. They're all abelian. This is a abelian state. Okay, and so D is the square root of 4 or 2. Okay? So we want to prove that this quantity, this conditional mutual information, is greater than log 2, or conditional mutual information is greater than 2 log 2. Okay, so how does the proof work? The idea is, it's just going to use, as I said, strong subadditivity. But the idea is we want to slightly generalize the class of states we think about. So here's my 4 regions. Instead of just thinking about I'm interested in the case, in the ground state, right? But what I'm going to slightly generalize and think about states where I have an anion in the center and another anion out here, okay? And so let rho A be a state with anion A in the center of the anions. So it's the ground state, if you like, the ground state acted on by a Wilson line operator or string operator. So our goal is to prove the following equality. So our goal is to show that the conditional mutual information in a particular state is greater than or equal to 2 log 2. The reason there's a 2 here is because remember our definition had a 1/2. Okay? And which state do we want to prove it for? We want to prove it the state with no anions. So that's in this notation, that's the state rho 1. That's what we want to prove. Okay? So so how are we going to prove it? What we're going to do is we're going to consider we're going to use strong subadditivity. And in particular, I want to consider a mixed state, which has a mixture of different anion types A. So I'm going to consider a mixed state. Which is of this form. PA rho A. So it's a mixture of different states. You know, these PAs are probabilities, right? So the sum of the PAs is 1. They're all greater than or equal to 0. Okay? So consider some arbitrary mixture of states. By strong subadditivity, we know this quantity is always greater than or equal to 0.
The quantity on the left is always greater.
Always greater than or equal to 0. The conditional mutual information, very generally, is always greater than or equal to 0. And I'm going to use it. I'm going to consider it in the particular case of this mixed state. In that particular case, among other cases, it's
Rho
greater.
A is the label of the anion.
Yeah, rho A is the that's rho A. That's right. Lambda is a mixture of the rho A states. So I want to consider a mixture of different anion states. Take the conditional mutual information in that state, and then that has to be greater than or equal to 0. Does that make sense?
So rho A is a density matrix of a pure state.
Rho A is a you could think of it as a pure state. Yeah. I mean, if you want to think of this on an infinite plane, you could also think of it as a mixed state if there's like some. It's just a patch.
Okay.
It doesn't
where
matter.
you trace out.
It doesn't really matter, whether it's pure or mixed on this discussion. But yeah, I would think of it as a pure state. Is that okay? Okay, so strong subadditivity implies this is greater than or equal to 0. Now I'm going to show you this already gives you some bounds. It doesn't quite give you the bound we want. So almost, I'll say it's halfway to the bound we want. Just this. Okay. So let's. So to get from here to here, I have to relate the conditional mutual information in the state lambda to the conditional mutual information in the state rho A. Okay, for some A. So let's try to do that. Okay, so what we're going to do is first, remember the conditional mutual information has like 4 terms in it. Let's start with actually what you might call the hardest term. Right, so this is the entanglement entropy of lambda of the whole state ABC. So let's try to relate this to something involving rho A's. So to do that, well, we can just write lambda. Lambda is the sum of rows, so lambda ABC is the sum of rho ABCs, right? So I can write this. Okay, that's just replacing lambda, basically, the sum of rows. And now what I know, this is where I need to use something about anions, is that these density matrices are orthogonal to each other. What that means by orthogonal is that, you could say the trace of this against rho A times rho B is 0. And why is that true? Why are they all orthogonal? Well, it's because, I mean, this is an assumption you say, but I'd say it's almost a defining property of anyons, is that if you have different A's here, different anion sectors can be distinguished, right? There's some operators, like for example Wilson operators, which will uniquely distinguish the different anion states. So different sectors are eigenvalues. There's certain operators you can write down here. There are going to be eigenvalues of those eigenvectors of those operators with different eigenvalues. So all the Schmidt states in any given anion sector have to be orthogonal to all the Schmidt states in another anion sector because they're all distinguished by some Wilson line operator that lives in ABC.
There's an assumption they're independent, so you can always orthogonalize them, right?
No, I'm not orthogonalizing them. I'm claiming they
You're
are
saying
orthogonal.
that they are, so
yeah.
By definition.
They have to be orthogonal. They can all be distinguished by some measurement within ABC. That's basically the state. There's a.
But you need an operator whose eigenvalues are the simple anyons.
Yeah, that's right.
That's not clear that it's true in a general non-abelian theory of anyons.
Yeah, you can construct projectors onto the different anion types by taking sums of Wilson lines multiplied by like roughly the S matrix.
You need to invert the S matrix and multiply by the
Yeah. So these are orthogonal. Now, when you have a linear combination of density matrices that are all orthogonal, the entanglement entropy can be written as a linear combination of the individual entanglement entropies plus an extra term. So this is just a general fact about orthogonal density matrices. You can always write the entanglement entropy of this, or the von Neumann entropy, I should say, of this density matrix as a linear combination of the von Neumann entropies of this plus an extra contribution, which is the Shannon entropy associated with this probability distribution. By Shannon entropy, I'm denoting by H of P. This is just the usual, P log E thing. Okay, so that's just a general. Once you assume they're orthogonal, that's just a fact about von Neumann entropy. And now that's just one term in that sum of 4 that appears in the conditional mutual information. So let's talk about the other 3 terms. Those are even easier. So let's suppose we want to look at S of lambda AB. Okay, so if we look at S of lambda AB, again, we can write that as S of the sum of PA rho AB. That's just substituting what lambda is. And now there's something different. These are not orthogonal density matrices. In fact, I claim these are all the same. So why is that? Well, now we're not looking at the whole ring. We're just looking at part of the ring here. And so it doesn't, any anion type you have here, they all have exactly the same density matrix here. One way to think about it is I can create this excitation by a Wilson line that totally avoids the region AB. Right? So it doesn't disturb the density. So this is this is what you have when you have flexible string operators. You can move that string wherever you want. So any region except for these regions that encircle A, the density matrix has to be the same in all the different anion types. In other words, you can't detect an anion by just doing a measurement in region AB. You have to do the measurement in the whole circle. So because of this, because I can get from any state to any other state by an operator, that avoids, say, region C, all of these density matrices are the same. So that since they're all the same, I can just replace this with A equals 1. Like in particular, A equals 1, the probabilities add up to 1. So I can just write this as AB1, right? And now, I'm going to try to write this. I want to write it like this, like some kind of linear combination of S of rho A. So I'm going to do some manipulations just to put it in that form. So I can, this is kind of, might look unnecessary, but I'm going to just write this as the sum over A, PA. I can do that because the sum of the PAs is just 1. Right? So I haven't done anything. And then the last thing is, again, I use the fact that they're all the same. I can replace rho AB of 1 with rho AB of A. So you can see the end result of this is a formula that looks almost exactly like this formula. It just doesn't have this extra term, right? So all the other regions, every region except the ABC region, that von Neumann entropy is just a linear combination of the individual points. So this is also true for lambda BC, lambda B. Okay, and so when you put the four terms together, remember we have to take a sum of four of these terms. When we put the sum of the four terms together, I'm going to get, I'm just going to get a linear, the conditional mutual information for lambda is just going to be a linear combination of the conditional mutual information for row A's. Right? This is happening in every term, but there'll be one extra contribution, right? We have this one extra contribution that comes from the ABC term, and it comes in with a minus sign. This term has a minus sign in front when you do this. So I'm going to get an extra, just one extra term, which is the Shannon entry. Okay? So now I've succeeded in what I want to do. Conditional mutual information lambda is just a linear combination of conditional mutual information of the row A's minus the Shannon entry. Yeah.
Just check, I guess the place where you use the Tory code is that sub index A is set to 1 because for Elin anyons doesn't matter. Like you still have A there, right? Is that the
I mean, what I'm saying here, actually, this part of the argument works for any anyon theory. It's not specific. So this first half of the argument is very general.
I see.
I haven't used.
But so from this side to there, you plugged in 1, or is it still A? Sorry, can.
Over here, I put. I first put in A, and then I replaced A with a 1.
Right.
Yeah. So if what you're asking is, have I used anything specific to Tor code? The answer is no.
Oh, I see, and then back to A there. Okay.
This is all very general, actually. It's the second step of the argument, which uses something slightly more specific. All here, the only thing I'm using is, the only two assumptions that I'm using is that these are all the same density matrix, and these are all orthogonal. That's a very general statement about any anyon theory. So far it has really nothing to do with the Tor code. Okay, so what's the end result? I've written down this conditional mutual information. I know it's greater than or equal to 0, so I get inequality. Okay, so let me write down the inequality. The inequality is the right-hand side must be greater than or equal to 0. So by SSA, I get the following inequality. This is greater than or equal to 0, so I'll write it like this. The sum over A of PA and I'm going to box this, because this is half of the proof. Oh, no. This I'll call this inequality star. This is very general inequality. It should hold for any anyon theory. And let's see what that tells us. That almost gives us, it gets us halfway where we want to go. Let me show you why. Okay, so let's use this inequality. It works for any probability distribution. So let's pick the kind of maximally mixed probability distribution, which is the one you should use for the Tor code, because it's that abelian state. Okay, and if you do that, so you choose all the probabilities equal to 1/4, what do you get here? You get 1/4, and I'm going to write this in like abbreviated notation. This is the conditional mutual information for each anyon type. I'm just going to write that as like I sub 1 plus I sub E plus I sub M plus I sub N. That's what appears on the left-hand side. It's a linear combination of these conditional mutual informations, which I'm just abbreviating by I sub A. That's what you get on the left-hand side. On the right-hand side, this is the Shannon entropy of this thing here, which is just log 4. Okay. You may remember what we were trying to prove was that I1 is greater than or equal to 2 log 2. This is the predicted value, right? We wanted I1 to be greater than or equal to 2 log 2. Here I've shown the average of the I's over all the anyon sectors is greater than or equal to 2 log 2. So that's why I say it's halfway there. It's halfway there because we wanted I1. Here we've shown some kind of average over anyon sectors is greater than or equal to 2 log 2. But in principle, I1 might be less than 2 log 2 and these could be greater, right? So we have to do more work to show that I1 is greater. And I'm out of time. So maybe I'll just write one inequality on the board. I won't have time to derive it for you, but I'll tell you what the second inequality, this is inequality star. The second inequality, which you can also prove just using strong subadditivity, is this. Okay, I have to draw a picture for this. So A is the annulus we've been, just draw a picture. Then I'm almost done, I promise. Okay, so A would be this big region. What is A prime? A prime is like a slightly smaller region. Maybe I can draw with a dotted line. This is A prime. Okay, so the claim here is if you can calculate the conditional mutual information on annulus A, and you compare it to the, in some anion sector little a, it's always greater or equal to the conditional mutual information on a slightly smaller annulus A prime in an anion sector S cross A. And S can be any anion. I mean, I'm skipping the steps for how you prove this, but it's actually just a few lines for also conditional mutual information. But you can prove that the conditional mutual information in anion A is greater or equal to conditional mutual information in S cross A on a slightly smaller annulus. And why does that help us? So given that, I can just prove it for you in like 2 lines.
For arbitrary S, that's like.
Yes, for any S. I mean, maybe I should just hint at where the proof comes from. I'm not going to explain it, but maybe some people will see it. You draw a Wilson line, involves an S and S bar. That's all I'll say about it. I can explain afterwards if people want to know where it comes from. But anyway, suppose we've given this. Let me show you how you would prove it. And this time I'm going to use this board properly. So how would you prove it? So what does this mean? If you use abbreviated notation, what this means is I sub A is greater than or equal to I of S cross A. I'll put a prime here. Okay, so this just means conditional mutual information on the big annulus, this conditional mutual information on the small annulus. So that's just, I sub A is just the shorthand for that. It's the same shorthand I used, that I used over here. Okay? So, what does that get us? So that allows us, so if we apply this inequality, we can get the following results. I1 is greater than or equal to I1 prime. So the conditional mutual information, this just follows from taking A equals S equals 1. We also have I1 is greater than or equal to IE prime. That follows from taking A equals 1, S equals E. And then we have I1 is greater than or equal to IM prime. Same logic. It's like A equals 1, S equals M. And we have I1 is greater than or equal to IEM prime. So in other words, I1 is greater than all the other I primes on smaller annulus. And now we're done because we can say I1, since it's greater than all of them, it's greater than their average. And the average, I proved over here. Remember, this holds on annulus. It holds for the primed annulus and the unprimed annulus. The average is greater than 2 log 2. Okay, so so this is kind of the sketch of the proof. I didn't get to prove the second part for you guys, but if people are interested, I can explain to them. It follows from basically strong subadditivity. Almost no further assumptions, basically. And again, you do have to assume that you can fuse 2 anions together. I guess I have to explain that. But it's essentially comes from simple assumptions about anions. You get this inequality, and then you get this.
So did you use this toy code?
Sorry?
Did you use this toy code?
The which?
Did you have to assume it's toy code?
No, really, I mostly just used it as a abelian. So, I mean, what I was going to say here is the same proof works for any abelian state. The same proof works for any abelian state.
You is this related to the fact that for abelian anions, SS bar string can be created by finite time?
No. The only thing is, the only way it uses abelian is just that S cross A gives you a definite abelian sector. For non-abelians, of course, if you take S cross A, you'll get a superposition of different sectors. So in the non-abelian case, you have to slightly generalize this inequality. I call this inequality star star, and I won't explain that here. But there's a generalization of this, which you can write down. It takes a few lines, and then using that generalization plus this and a little bit more work, you can also prove inequality.
So this inequality is true for both abelian and non-abelian.
That's correct. That's correct. Yeah, but I'm not going to prove it in the non-abelian case 3. But I'm happy to explain to people if they want to. Interestingly, in the non-abelian case, one comment I just want to make is in the abelian case we had to use this trick of using a slightly smaller annulus. I didn't quite explain how that comes in, but in the non-abelian case, it turns out you have to iterate it. Like you have to go smaller, 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 smaller. So you have to you don't get quite as clean an inequality as this. You get an inequality that looks like I sub 1 is greater than or equal to log D plus a term that scales like how many times you iterated it. So you can get 1 over square root of n. So, minus. This is some order. You get something like this. And so what this means is that I think this is maybe a limitation of just the proof. I have to actually assume that my annulus, I can choose smaller and smaller annuluses, at least n of them. So that roughly means the annulus has to be n times the correlation length or something to get this inequality. So if you like, this is sort of saying I can prove the inequality of a bound like this, where n is roughly the size of the annulus. But in the limit of very large annuluses, this will go to 0.
All sizes should be.
Yeah, but in the abelian case, interestingly, I think this is some kind of technical thing about the proof. Maybe there's a way to get rid of that. But in the abelian case, you don't have that. You just have to do it once, and it gives you the inequality immediately. Anyway, I think that's it. Is there anything else I should say before I finish? Yeah, I'd say that there are 2 open questions. One is whether this bound holds for the Kitaev-Pressfield definition of gamma, which is another partition. It doesn't look like this. And the other is whether the bound is saturated generically. So there's some belief in the community that you actually get equality generically. That these examples that we've shown are kind of non-generic. They require fine-tuning. That's also an open question that would be interesting to address. Sorry for going over.
Okay. Any emergency questions? No, you can. I mean, we have time for maybe 2 or 3 questions if they're not too long.
Okay, I have a non-emergency question. What's the simplest example with Z2 topological order in plus 1D that actually violates the?
Oh, you could just take the cluster state and stack it on top of.
Without breaking translation invariance.
You could take the cluster state, the 2D cluster state.
Oh, sure. Okay.
Yeah. Well, you have to do it on. I can show you on a particular lattice. The cluster state on a particular lattice, 2D lattice. If you take weird cuts, gives you this log 2, and then you stack that on top of the tool code.
Okay. Cool. Thank you.
For non-linear anions, like Timothy why this log D might be in proof, I would say it's something like log number of anions.
Oh yeah, well, so there's a couple differences. In the non-abelian case, first of all, somehow the maximum, how should I say it? Yeah, that's a good question. So this bound, this log D, this is the extra information you have. One way to think about it, it's the extra information you have from knowing that there's no anion in the center here. That's where this log D comes from. Okay, it's like the extra information from knowing that the center is in the identity anion. When you have non-abelian anions, that's more information because they're actually more likely to have. Having a non-abelian anion here is actually a more likely thing. If you consider like you heat it up to some high temperature, and you look at the probability distribution of anions here, the non-abelian anions will occur with a higher probability. In fact, it's proportional to their quantum dimension squared. They will occur with a higher probability than the abelian ones. So knowing that when you have non-abelians there, not anions there, knowing that there's attributing anion there gives you more information than just the number of anions. Yeah.
Are there any examples of spurious TE without having to deal with SPTs?
That's a good question. I don't know.
Okay.
You said this proof is unpublished.
That's right.
So if you're fast, you can.
I would like to put it out maybe in the coming months. Yeah. I think it's a useful alternative proof. Yeah.
You just use the inequality that the initial mutual information in this mixed state, like, is greater than or equal to this H of rho A.
Yeah, I use that this is greater than or equal to 0, which implies this is greater than or equal to this.
Right. How do you see that the greater than or equal to part comes from like SPTs from this kind of?
Comes from what?
Like SPTs, lower dimensional SPTs from this kind of proof. Is there a way to see where the source of?
I don't know. This inequality doesn't tell you anything about the source of it. It just gives you a bound. Yeah.
Can I just very quick outlook question, and maybe you can also get some debate going later on in the conference, is, are you still hopeful that there exists an invariant that's really invariant under finite unitaries, or are you starting to suspect it might just
like a clean one? I mean, you can always make an invariant. I
no,
mean,
but not by going over the space of unitaries and trying to minimize.
I don't know. I would argue even for symmetry breaking order, we don't have that. That's sort of what I was trying to say.
Mm-hmm.
Like for symmetry breaking order, we say, oh, order parameter solves the problem, but actually order parameters only give you a bound. So I kind of wonder if that's kind of a limit. Yeah, that we shouldn't expect for more.
Okay.
Yeah.
Can I still ask a question? It's short.
Very, very short.
So do you think it's possible to have, besides the spurious topological entanglement entropy, but also a spurious chiral central charge coming from the so-called modular commutator?
Yes, it might be. Might be. I can talk to you about it.
We'll have a 3-hour lunch discussion break. And, tables are quite big where we're going, so you can just